Hi everyone. In today's video we're going to be showing the procedure on how to estimate agricultural water demands. So basically at this point you must be somewhere here in HydroLearn, or you can also see it on the PDF Google Doc file. And as you're going through all of these exercises, at some point you will have to calculate the effective crop evapotranspiration. So you'll have to take a look at this template of the file, the detailed instructions that I already opened them here, and some of the template of for submitting this. Now, once you have this file open, which is continue to open, just make sure to save it, save a copy as, and then you're gonna put it in here. Let's do this, make a copy, and what I am going to do is and I'm gonna put it in here, okay? I'm gonna have it like agricultural demand and my name. Okay, so that will take some time to reload. So in basically in this exercise, what we're gonna be calculating first is, well, we will talk about reference evapotranspiration, crop coefficients, then in this case that will be crop evapotranspiration. When you subtract the precipitation, that will be effective evapotranspiration, and then you divide it by the applied water, and that will by the irrigation efficiency, and then you will calculate the applied water. So that will be the overall flow of our exercise today. Something that I'm going to do is I'm gonna have this window on the side so we can actually see what are we working on. Okay, great, so we are there. So this is what I was explaining. So basically we're gonna first have, this is the reference evapotranspiration, then the crop evapotranspiration is the reference times the crop coefficient, and then when we subtract the precipitation, then we're gonna have effective crop evapotranspiration. Once we have done that, then you will calculate that. Then in order to get applied water is to have our effective times the area of production divided by the irrigation efficiency. We call it here application efficiency, and that will give us the applied water, the water that the water for that specific agricultural demand. Okay, so let's go back here, and basically what it will tell us here is that this is the historical agricultural use of water in Pajaro Valley, which is what we are seeing here. Then basically, and here down here you can see the total acres. So what was the acreage of all these different crops, and we can see how the production of strawberries has increased, vegetables have actually decreased, raspberries, blackberries increase. Now we have some wine grapes, artichokes have decreased, apples and the apple orchards have decreased. And remember that Watsonville is where the Martinelli ciders are produced. So yeah, a lot of that has gone and converted into different crops. Nurseries basically has been around the same, and other things. Okay, so let's go here to the crop evapotranspiration, and the first part will be to plot these crop coefficients. So basically the way that we can do this is Google Sheets doesn't like to have the cells merge. So I had to merge, and one easy way to do this is just to select the data, including the header. Typically will be the title of that specific data set, and then here insert a chart. It will come here, and then in this case what we want to have is not like that. We want to have it as lines, right? And when we have those, we are gonna add the x-axis, and the x-axis will be here, the months. So now we have those there, and that should do it. We can have here the legend, put it at the bottom, and now we have it in here like this. And let's just close this one. So our first axis, and basically what you're seeing here is how different crops have different crop coefficients. Remember that the crop coefficient is how you are changing the factor from reference evapotranspiration into a given crop. So it is the conversion factor from that, from a well-watered grass to that part. So I'm just gonna leave that. This is what I'm gonna put it somewhere here, so it is out of our way. Okay, now, so now we're going to be doing, we're going to be calculating this effective crop evapotranspiration, and we're going to go to this cell and actually use this formula, and I will explain what this formula is about. So this will be cell E29 here. Okay, so let me just put it in here, and this is what is happening. So we're multiplying. So remember that we have ETO times KC. In this case, this cell C29, this is the reference ETO, and you can download it from CMIS, times the KC. In this case, we want to have the KC value, the crop coefficient value for strawberries. So what this VLOOK formula is doing is basically saying, okay, I want you to look for the value number 1, which in our case is month 1. You will go to this table, which is this table here, and we look in this first column for the value 1. Then you will move what is the column that you want to retrieve, and in this case is the second column, which is the one for strawberries. That's why we put the number here too. And false, it means that we want exactly that the number 1 here that we're looking matches the number 1 here that we're looking. If you put through, it will go to something close, and then we're subtracting the precipitation. So the first part is the crop evapotranspiration, and the minus precipitation will be this part when we're subtracting this. Now this is minus 17, so we're having a minus reference minus effective evapotranspiration. That is impossible. We're having minus millimeters. What that means is that this first portion, which is the crop evapotranspiration, so the KC, the ETO times the KC, this value is lower than the precipitation. What that means is that precipitation in this case is covering for the entire crop evapotranspiration. We don't need to actually irrigate, because all the water that is needed by the plants is used by the is provided by the precipitation. So what we're going to do is to add this max of 0. So in here we will go here and we type max 0, comma, and basically then we're going to be capping that. Okay, so ta-da, we have that. And now what we're going to do is to copy this and apply it for the rest of the crops, and then we'll apply it for all the time series data from January 1st all the way to January 2050. And then we can discuss how actually that one is possible. So basically we are copying this reference evapotranspiration, these values, after 2020. So this exactly time series, we're saying that the same time series will apply. So look at this. When we go to here, you can see that exactly at 2020 we are repeating that. I think it's this one. I think we have data until 2020. Here, 2021 we are repeating the data. So 0. You can actually see here that it is doing that. So in 2021 we are now referencing the cell C29, and C29 is this one. So then in 2021 we are repeating this reference CTO. We do not know what is going to happen in the end, but we know we are considering that we're going to have similar conditions, and then we can discuss about it, if how that is effective or not, considering climate change and things might not be the same. Anyway, so now we calculated this. If you look at here, so strawberry 0, 0, 0.15, 0.3, 11.28, 46, 39, 22. So you can see that values are about the same. Here, see, 0.05. Here we have a 0.12, 0.11, 0.05 in here. So things seems that they are working, right? So we have here a 0.1, here 16, 21, 22, 21. Okay, so it looks like this is working. Now what we're going to do in here is so what are the reference evapotranspiration conditions during a wet, normal, and dry year? So we're going to use this equation here. So here we can hit this, and then you have to press Ctrl Shift Enter and then enter again. So, oh, sorry, there you go. Ctrl Shift Enter, sorry, here, Ctrl Shift Enter and then enter again. So basically, because this is an array formula, what this is doing here, we are trying only to collect on this column only data with month number 1. So basically this is what it's saying. If this is equal to 1, which is this value here, if this is equal to 1, then grab this value. Otherwise it will be empty. And then obtain the percentile. In this case the percentile is the 25th for that time series data. So here is basically calculating the 25th percentile of the reference evapotranspiration for month number 1. So we have that one there. Then we can do the same here. And then we can calculate it for the different percentiles. Now here, there we go. Now this one looks. So here they are, just kind of double checking our numbers. It seems that we are doing good. So basically these are, so notice that the reference evapotranspiration, the value of a well-watered grass, how many, so in whatever area that you're thinking, if you're well watering a grass, it will evaporate in a normal year 3.5 feet. 3.5 feet is about 90 plus 15, so 1 meter and 5 centimeters, 105 centimeters or 3.5, and it can go to from 330 to 338. So we have now these values here. Ta-da! Okay, so ta-da! Mm-hmm. Mm-hmm. There we go. Mm-hmm. I just want you to show you that I'm just doing that until there, and then this one here. There you go. Okay, so that will do it. Now what we need to do is, so we're gonna put here, now we need to calculate the reference evapotranspiration, but for strawberries, and later putting it in here. So basically what we can do is to multiply this normalized average value times their crop coefficient. And what it will happen here that you're gonna see is that you can actually see that growing strawberries, it uses 2.8 feet of water, and having the grass well watered is 3.6. So if you well water a grass, regardless of the area, you will have to flood it in a year, that area at 3.6 feet, 105 centimeters more or less. And in this one, you will, for growing strawberries, you actually have to flood it less, 2.8 feet, which is, that is about 90, like 85, 80 centimeters. So just to give you a comparison of that, then what we're going to do is to actually finish this one, right? So we can estimate all of this, and in this case what we can do is to fix it to this column, to P. So I'm just gonna add there the $sign. This is the same. I think this will be that. There we go. Which this, what I did it here, is what it was say there. Hey, I was just remembering what my step. So you can actually compare that A well water grass uses 3.6 acre feet, 3.6 feet of water in whatever area during a year, and you can see that the remaining is actually quite less water. Another way of thinking why we need to get rid of the grasses. So now for this one, to calculate the wet 25 percentile, let's actually so we can use this formula. In note 29, which is here, to calculate the 25th percentile value for all the Januaries, and in this case will be for strawberries. The column that we are analyzing is this, so that's why it is in this bracket. So when the month is 1, January, basically what it's doing is only getting values of only the months 1. Otherwise, the matrix is empty. That's why it has these 2 quotation marks. And then otherwise it takes this value. So basically we're getting that, and the percentile is 25%. So this is not calculating anything because I didn't do the control shift. This is actually an array. So once I'm here, control shift, and then enter. So that's why it was not calculating before. Now it is actually providing numbers. And that's when it says this is an array formula. When you hit control shift enter, you're telling that it is an array formula. So this is an array, is a matrix, is a vector. So now that we have that, we can copy our values here. And you can see that we are close enough, okay? 2.1, 2.01, 161, 0.25, 0.26, which are these ones. So I think we're actually pretty good, right? Now, something also for you to notice is that if we didn't have any rain, this will be how much water the strawberries needed, 2.8. In this case, because we have some rain, you can see that January, February, November, December, there is no need for irrigation, and very few in March. Actually, strawberries need water on those months. However, as you can see here, in many of these months, actually rain is supplementing it. You can see that during the drought or during hot years, now water is needed since February until November, and that the total value is less. So rather than requiring almost 3 acre feet of water, 2.8, now you need only 2 feet of water, which is 60 centimeters rather than almost 82 centimeters. So you will have to do the same. Well, now what you're going to do is to create a really nice graph that actually looks like that. Ta-da! And now it really wanted to now actually have the names here, not as the previous one. Yep, and you will have to change the colors and so on. But basically that's how you can do this. Just gonna leave this one here. Okay, there you go. And now, you will have to calculate for the rest of the. You can use these formulas in all these different corners too. To do that, please remember to hit Control Shift Enter and then again Enter. Okay, so it knows that. Okay, now we're gonna calculate applied water, and we already have the effective evapotranspiration, and we need to multiply times the area over the application efficiency. And this is for a given time, for the same time, and for the same crop, and then this should be effective. Okay, so let's go here. And these are some of the application efficiencies or irrigation efficiencies that we're gonna see here. You're gonna see that those values are actually explained here. So these are the application efficiencies for a certain time, period in time. And then after that, some of those have increased or decreased. And this is the acreage factor. So basically what we're saying here is that this polygon, well, we have the area recorded is the area of the property. They are actually not growing crops in all the property, actually in 77% of the property. So basically we are only considering the effective area of production, not the property area. So that's why this acreage factor, that's what this means. Okay, so you can also see that we're gonna calculate it for two different places. One will be inland, which is, let me see if it explains it here. This is the inland portion, so east to Highway 1 and the coastal area. So this is the acres, this is the area for that. This is the area for that other one. Okay, so, and again, we need that area because remember that our equation will be multiply that effective evapotranspiration times the area divided by the application efficiency. Okay, let's go back here. So, to calculate the future area, what we're going to do is we go to this seal B45, and basically we're going to estimate for 2021 the average of the last 10 years. So we're going to use this formula to calculate in here the average of the last 10 years for the future. So basically what we're considering here is that we're going to use this value as a reference, and we're going to consider that on average those last 10 years that acreage will be continued until 2050. This is for inland. We can do the same for coastal. And now that we have these two values, basically we're gonna say that these values will be the same for, again, all these crops and for the following years until 2050. And we can do exactly the same for, in this case, this is inland, the coastal region. So as you can see here, in this case, this 2403 and 2,403 acres, or this 2,197, they match that part. If we get a closer look here, you can see all these different areas. So in this case, these values are 2403 and here we are. There you go. So these values here, you can see that are the same that we estimated, and it's just repeating that. Now we're going to multiply this effective crop evapotranspiration that was in the previous sheet times the area. So we're going to look, this vertical lookup is for looking the area of that specific year times the acreage factor. That acreage factor is in here. And you can see here, if it is less than 1998, then use this one, right? Less or equal than 1998, use this value. Otherwise it will use the other one. Divided by the application efficiency, and the application efficiency is here, and it depends on the specific crop. Okay, so we can actually do that, and it is this very long equation. And you can say like, no, it's not. Yeah, you can see that one was hidden there. Okay, so now it's going back to the crop evapotranspiration times the area times the acreage factor, and this is divided over that. So I think that will do it. Here, there you go. Ta-da! So because there is actually it's until here, so we need only just to work until here, which is inland. Right now we will be calculating that. Then it went all the way down. So what I did is that once all of this is selected, when this change the cursor into that cross, you double click and it will calculate all the way to the bottom. And this will be the equation, but for the coastal region. So in this case we need to go back here and calculate this for the coastal region. There you go. And just in case, I'm just making sure that it is all of this that is multiplied is divided by that application efficiency. So we'll go here, then all the way down, and then the total should be, yes, just zoom in all of this, right? From C83 to R83. There you go. Now that is there. Ta-da! All the way down. Now we need to go here and make a summary of how much of the applied water was used by strawberries and so on. So basically here in this cell, in B14, what we are going to be doing is using this large equation. Yeah, and basically, I'm gonna explain it here, but what this is doing is summing, actually hit enter and then here. Okay, so it will sum these values of column C if these values in column A are equal to, in this case, 1990. Okay, which is the value here. And then plus it will, so that will be for inland, right? And for coastal we'll sum these values here every time that this is, the year is 1990. So basically that's what it's doing, is summing all the values for 1990. So here we are. So 13,383. And we can copy it all the way there. So 2690, 2659, 963. Here this one is 4179, 585. So we have that one there. Then of course we can always do here the sum of all of this. And now that we have all of this, we can just double click in there and that will do it. You can see that here we have that 1300, 17,297 to 254, 9,343, 121, and so on. So then we are good. So the last thing here is that we need to have this one as what is the water use, the agricultural water demand throughout that year. So basically something that we can just say here is total agricultural demand, and then select this one. There you go. So we have that for the X series. Sorry, give me a second here. I'm just gonna get rid of this. I'm putting here. There you go. Edit. So rather than a line, I'm gonna put column. It's just only one, and then here it will be this guy here. Sorry. There you go. Okay. Ta-da! And then you can change, of course, also the title there. Then the seasonal variation, and what I want to know is how these things change seasonally, right? So here we have how much water is used under that. So we're going to this AG13, and then we're gonna use this. And basically what it is doing is every time that the month is 1 January, it will go into this Well, here is, let me actually just click enter here. Oh, there you go. So it's going here to these strawberries. Every time that is 1, it will get the average of that. Plus every time that this month is 1, it will get the average of that value. So that will be this guy here. This guy. And then so this is how much acre feet are used on average on January for growing strawberries in Pajaro Valley. And then here, of course, we can hit this. There we go. Which is this value here. Okay. There you go. And all the way until here. This is actually not correct. So once we're there, we just need to and this is so in total on average is 42,000 acre feet of water in this region. Now here is only for that. You can see that is the value that we got in here, and now we also want to have the precipitation there. Oh, I see how this is happening. Okay, so let's actually calculate now the average precipitation. In here we need to go to second, here, AP13, which is here. Then we'll go here. There you go. Basically, this will do exactly the same, do the average for only for the Januaries, but on the data of crop evapotranspiration and in the columns, well, it will use the months in B, column B, only for applied. So for the months of 1, it will only select only the 1 month of the column D. And basically, if we go back here, in this case, column D is precipitation. So it is coming back and doing that analysis on this sheet. So if we do that, sorry, there you go. Okay, now this one, so what I am going to do is to give me a second. Okay, so let's do this. And then stack, and we're getting something close to this. Now the labels, gonna put it at the bottom. It's looking a little bit better. And give me a second. This guy. So for this, actually I want to have it on the right axis, on something different, because right now the precipitation, we cannot see the precipitation. And actually I'm gonna have this one at a very light color. Okay, let's have it a tiny bit lighter. Okay, so now we are seeing that all these different other crops, and then how it is compared with evapotranspiration. Here unfortunately I cannot change this one here to switch it from a column into a line, but a trick that I just learned. So something that we can do is to insert a drawing, and then here in the drawing I can paste, sorry, there you go, that is specific. So I hit Control C on the other one, on the chart, and then I'm pasting it here. And what I'm going to do is I'm going to do this manually. So basically I'm going to create a line of the, sorry, this one that is called polyline. And then I'm just gonna put it at the top of the bar columns that I put it really, really light. So this kind of gray color that it doesn't show. So once I have that one, what I can do, sorry, is that I can make it a little bit thicker, and I can make it like that. So it really resembles this one. And what you can see here, the main point of this is the following. Precipitation, when we have precipitation, we don't need that much water. During the summer, when precipitation is gone, then that's where we have most of the water uses. And then once where the growth is going down, then it will be something like this. Okay, so now when I hit 7 close, ta-da, you can have a graph similar like that. Let me see what else is here. Okay. Really large file. There you go. I'm just kind of moving everything on top of it. It's on top of the tables. Oh, here, and basically here for strawberries, what we want to know is the applied water, the typical applied water. So in this case, we'll go to the cell B83. Let me see. So let's go here to cell B83, and let me just have this tiny bit smaller. So this is what we're going to be doing. And basically we are just gonna compare how now with the applied water, how that previous effective crop evapotranspiration now is converted into applied water. So that's basically what this is about. So we have that one there, and then we have that one there. Mm-hmm. 2.15, 2.68, and so on. Which you can see that this is different of this one, that it was 1.6, 2.0, and 2.4. So these values here, if we compare them with the previous one, with the applied water, they are less. And why they are, there you go, I just hit Ctrl+Shift+B, so I only have the values here. But what you can see is that this is the effective crop evapotranspiration. So once we have taken the precipitation, and how because the irrigation systems are not that efficient, then that's why we need to, instead of applying, let's say 2 feet of water over a given area, so in a year, we need to apply 2.7 feet over an area, and that is because of the irrigation efficiencies, that we need to over irrigate to actually meet those water requirements. So that would be it. Thank you for watching. Now, if you want to know how to do these extra points, this is actually pretty easy. And there are a couple of ways of doing it. So in this case, we want to compare 1999 with 2020 data. In here, I know that by now, I mean, remember that in the previous exercise, we were thinking like, how can I verify that the work that I'm doing, it actually matches the observed values? In this case, with all of this procedure, we have estimated the applied water. And basically here what we want to do is to compare it now with historical data. So in this case, this total applied water from 1999 to 2020, this one here, we are going to compare it to these values, and I'm gonna put in here Control Shift B. So there you go, we have it in there, and I'm gonna put here applied water calculated and these are acre feet per year, and then this is measured agricultural water demand. Now I can actually plot these two here. And this one, I'm gonna put it like this, okay? Now here you can see that, so the applied water calculated, let me actually remove. Now let me get the x-axis correct. And the x-axis is the years, this one here. There we go. Now it's not that easy to see because it was here, but here I can put here years. So now we have that one. And what I'm going to do here is to, here I have the applied water calculated, and then here we can do this, the measured water. I have a typo there, I'm gonna, but there you go. This should be, there you go. So you can see that these are actually quite similar, right? This is one way of doing it. One way also to verify that. So you can see that actually they are pretty close. And if we haven't done that before, you can actually compare the numbers. So you can see that these are going pretty close one to each other. It's actually good because basically this is recorded data and this is the data that we are estimating. Now, also what we can do is we can estimate the R squared that we use in exercise 2 during our population calculation, and you can see that here if we estimate the R squared is actually pretty good. 0.96 is actually, both of those are pretty close. Another way to calculate this is actually to do this. So here we can insert a scatter plot and we'll see this one. Yeah. So that will be the data measured and applied, but this actually doesn't look that good. So what I'm going to do here is I'm going to the horizontal axis, and the horizontal I'm going to put the minimum 3500, which I think is the minimum value here. So minimum value was 39, so I'm just going to put it in there. Actually we can do, well, we'll see. We can do, let's say 35,000, and then the upper one I'm going to put 55,000. Okay. So now this x-axis is changing to that, and what I'm going to do, so that is the horizontal, and the vertical axis I'm gonna do it exactly the same. There you go. Now you can see that these are there. now we have exactly the same horizontal and vertical axis. Oh, here. So let me, on this one, also I would really like in the series to add a trend line that we know how to do it. And actually, I want to show the R square and I want to use the equation. Let me get rid of this. And now, I'm gonna copy this part, I'm gonna insert this drawing. Okay. And now, I'm gonna, so you can see that in the bottom is overestimated, at the top is underestimating. You can see that these two lines, they don't align pretty well. And that is okay. I'm gonna put it something like this. And this is another way. If this was perfect, both of them, all the dots will be along this black line. That will be the 1.0 R square. But you can see that it is not perfect. This is another way for doing this. I hope you have enjoyed. And see you. Ciao, ciao.